Yes, good morning, students. So in the last class, we have completed isomerism, right? So we have discussed two types of isomerism, structural and stereoisomerism. So in the last class, we have dealt with the stereoisomerism, mainly the geometrical isomerism and the optical isomerism, right? Yes. Fine. So today we are going to start with a new topic that is bonding in coordination compounds. Okay. What we are going to start is bonding in coordination compound. So what do you mean by bonding? Bonding means how the metal and the ligand, okay, they are bounded. Okay. So, so how the metal, so we know that in the center, what is present, metal is present, and around it, depending upon the number of ligands, okay, it form its structure. So if you have two ligands, so what it is, it will be a linear. Okay, if you have four ligands, so it will be a square planar or tetrahedral. So or okay, or if it has a six ligands, then it will have a octahedral. If it has a five, trigonal, pyramidal, or square pyramidal, like this, right? So these are the different geometry. So what is bonding? So bonding means nothing but the bond which is made between the metal and the ligand. So we are going to explain the bonding in coordination compound. So how this bonding is taking place, how this is metal and ligand are bonded. So that we are going to study. So how it explains the structure as well as the bonding in complexes. Okay, so that we are going to study in the bonding. So so depending upon that, so different theories are given. Okay, so there are different theories to explain the bonding in the coordination complexes or coordination compounds, right? So the first theory which we are going to discuss is the Werner's theory, which is that Werner's theory. So the first theory which we are going to discuss is, apart from valence bond theory, crystal field theory, okay, and molecular orbital theory, we are going to discuss first is the Werner's theory. Okay, what we are going to discuss is Werner's theory. So let us go for Werner's theory first, and then we will discuss the VPT and all. Okay, so okay. So there was a scientist, okay, there was a scientist named Alfred Wernerius quiz, okay. So he was a scientist who has put forth the Werner's theory. So the scientist was Werner Werneria, okay, Wernera quiz. So he was a chemist, okay, he was a chemist, and he put forward the theory, okay, of so by his name, Werner's theory, which explained the formation of complex compounds. So how the complex compounds are formed, so that was explained by the theory, okay. So it was first a successful explanation. So the whatever the Werner, he gave his postulates, he gave his theory, he gave his idea. So it became first successful, okay, so became the famous as the coordination theory of complex compound. Okay, so this theory which he has put forward, it had become so famous that it was named by his name. That was, it was given as Werner's theory. Okay, so the theory which he put forward, it was very successful and it was named by his name. So what are the main postulates of this theory? Okay, so each metal atom or ion in the complex, it shows two types of valencies. Okay. So the first point or the first main point or first postulate in Werner's theory, whatever the central metal atom is there. Okay. This is central metal atom or the ion in the complex. It will show two types of valencies. Okay. It will show two types of valencies. Okay. So first one was the primary valency. First one is called as the primary valency. Okay. And the second one is called as the secondary valency. Okay. Secondary valency. So what is the first postulate? So the central metal atom, okay, in the complex, it shows two types of valencies. First one is the primary valency, second is the secondary valency. Now, what is this primary valency? Okay, so primary valency is a ionizable. It is ionizable, means what? It forms ions. Okay, it will, if it dissociates in water, it will form ions. So primary valencies are ionizable. Okay, and secondary valency is what? It is non-ionizable. So primary valency is ionizable. Okay, so we will see difference between this. Okay, ionizable and secondary valency is what? Non-ionizable, means what? It do not produce the ions. It do not produce ion. Okay, so this is the first point. So in the central metal atom or the complex, what is there? It depends upon, it shows two types of valency. First is the primary valency, which is ionizable, and the second one is the secondary valency, which is non-ionizable. Okay. Then this primary valency which is there, no, this primary valency which is there, it will correspond to oxidation state of the central metal ion. So it tells you the oxidation state of the central metal ion. The primary valency, it tells you the oxidation state of central metal ion. Okay. And and it is satisfied by the negative ion. So how it is satisfied? Satisfied by negative ion. Okay, so this is about your primary valency. Then secondary valency, it corresponds to coordination number. It tells you about coordination number of metal ion. Okay, and this is satisfied by your secondary valency is satisfied by ligands. It is satisfied by what? Ligands. Now, what do you mean by oxidation state and what do you mean by coordination number, students? What is the difference? Can anyone tell me what is the oxidation state and what is the coordination number? Anybody? So I'll tell you. Okay. See here, FeCN6. FeCN6 3 minus. Okay, FeCN6 3 minus. Okay. So this is a complex. Okay. Now, considering this complex, can you tell me what is the oxidation state and what is the coordination number? Difference between oxidation state and coordination number? Yes? Anybody? So if you tell me the difference between oxidation state and coordination number, I'll then I can then I'll be sure that you have understood whatever we have said it till now. Okay. Okay, somebody has answered. 3 is oxidation state. So here, if I put x plus 6 minus 1 equals to minus 3, x is equals to minus 3. Yes, x is very good. Okay, good. So x is the, and coordination number is contain only ligands. How many number of ligands are there here? Coordination number means it tells you the number of ligand present. Yes, very good. Yes. So you have understood it. Very, very good. Okay. So oxidation state is what? Oxidation state, it tells you the oxidation state of the central metal atom. Okay. And coordination number means how many number of ligands are present around the central metal ion. It tells you the coordination number. Okay. So what does your primary valency tells you? So it tells you about the oxidation state and how they are satisfied. They are satisfied by the negative ion. Okay. How it is satisfied? You can see here how the oxidation number is satisfied. Yes. So which is there beside it? It is satisfied by the negative ions. Okay. And your coordination number, how they are satisfied? Coordination number, it tells you, it depends on what? It depends you upon the number of ligands, right? So it is satisfied by the ligands. Fine. And primary valencies are ionizable, secondary valencies are non-ionizable. So these are the 2 points, right? So what all we have studied? So the central metal ion in the coordination compound, it exhibits two types of valencies. First is the primary valency, second is the secondary valency. Primary valencies are ionizable, secondary valencies are non-ionizable. Primary valency, they will tell you the oxidation state of the central metal ion, and they are satisfied by negative ion. So we are finding the oxidation state of Fe, and what is there? It is so how it tells you, it depends upon the negative ion, right? Then what is the secondary valency tells you about? Secondary valency tells you about the coordination number of the central metal ion, and they are satisfied by the ligands. Coordination number means how many number of ligands are present around the central metal ion. So these are the points. So next one. Now, one more example, if I give you, so copper, NH3, 4, SO4. Okay, can you tell me here the first valency, primary valency, and the secondary valency? Yes, one more example, cobalt, Cl, NH3, 5, Cl2. Can you tell me the primary and the secondary valency, students? So which is the metal here? In the first one, the central metal atom is copper. Copper is +2. Okay, find out. So tell me what is the primary valency and what is the secondary valency here. So copper is the metal here, and here it is the cobalt is the central metal atom. Primary valency, it tells you about the oxidation state. So tell me the oxidation state of copper and cobalt. Okay. And what is the secondary valency? It tells you about the coordination number. Coordination number. Okay. Tell me. Yes, what is the oxidation state? See, don't get confused. Okay, if SO4 is there, so SO4 means what? If you remove SO4, okay, what will be the charge? SO4. So this can also be written as what? Copper, NH3, 4. Okay, SO4 is -2 charge, right? SO4 charge is -2. So it can be X plus ammonia is neutral molecule. So 4 into 0, okay, is equals to -2. So X plus 0 equals to -2. So X is equals to +2. So the copper is +2. So the what primary valency is +2. Then what is the secondary valency? What is the secondary valency in this complex? So how many ligands are present around the central metal atom? 4. So the secondary valency is 4. Yes, very good. Then second one. Second example. Second example. Okay, secondary valency is 4. Yes, Yamuna baby has answered. Very good. Okay. What is the second in a second example? What is the primary valency now? 2. Okay, let us see. Okay, let us see. See here. Now, how we have to find. Okay, don't get confused. Now here, cobalt, Cl, NH3, 5, and Cl2. Now, what is the central metal atom? It is cobalt. So X plus chlorine is -1 plus ammonia is 0. How many ammonia are there? 5. So 5 into 0 equals to, okay, so bracket is complete. So after that, you have to write equal sign. So each Cl is what? Each Cl is -1. So how many Cls are there? 2. So it is -2. Now you solve x -1 plus 0 equals to -2. X is equals to -2. So cobalt is -1. Here it becomes 5 into 0. It should be +3. The charge should be +3, primary valency, it will come +3. Primary valency is +3. And secondary valency, how many ligands are there? No. See here, how many ligands are there? Cl is also one ligand. Add that also. So 5 plus 1 is 6. So 6. Okay. So the number of ligands around the central metal atom is 6. So the secondary valency is 6. Okay. Fine. So this is about the primary valency and secondary valency. So this is clear. So let us go for the next point. Okay, so the metal atom or the ion in the complex, it has a fixed secondary valency. Okay, so the central metal atom, which is there, okay, which is present in the complex, it has a fixed secondary valency. Okay, so the coordination number is fixed. Coordination number is fixed. Okay, means what? So the secondary valency of the central metal atom is fixed. Okay, so either it will be in square planar complex or it will be in 6. That is a octahedral complex. So these two possibilities are there. So if there are 6 ligands, so the coordination number, the metal atom or the ion in the complex has a fixed secondary valency. That is secondary valency means what? The coordination number is fixed. Then, so this was the fourth point. Then the next point is what? The ligands bonded by the secondary valency to the central metal ion have definite spatial arrangement. Okay. So whatever the ligands are there. Now, suppose I have 6 ligands. I have 6 ligands. So these 6 ligands, they will arrange themselves in such a way that they will produce a proper geometry. Okay. And this proper geometry, it gives rise to different coordination. So it gives rise to what? So different geometry, different depending upon the number of ligands. Okay, it will give rise to different structures or different geometry. Okay. So for different coordination number, they will give you different geometry. So the ligands which are bonded by the secondary valency to the metal ion, they have definite spatial arrangement. You can see how the ligands are arranged themselves. Okay. So 4 ligands at the 4 corners of the square. Okay. And 2 ligands are at the axial position. So like this, they will arrange themselves in the spatial arrangement. Okay. So secondary valencies, they are directional. Directional means what? They have a proper arrangement. They have a proper spatial arrangement. So they are called as what? They are called as directional. Okay. And because of their directional, they can give proper geometry. Okay, they give proper geometry to the complex. While the primary valencies are non-directional. So the primary valency, it is non-directional. So this is the Werner's theory. Okay, this is the Werner's theory or Werner's postulate. Is it clear up to here? So these are the points. So if they ask you the difference between primary and secondary valency, so primary valency is what? It is ionizable. Primary valencies are ionizable. Secondary valencies are non-ionizable. Okay. Primary valency, it tells you or it corresponds to oxidation state. Secondary valency, it corresponds to coordination number. Okay. Then third is what? Uh, Primary valency, it is directional. Sorry, it is non-directional. Okay, and secondary valency is directional. Okay, so these are the main 3 points. Okay, and primary valency, secondary valency, okay, it is fixed. The okay around the central metal ion, and it will give you a proper spatial arrangement. So it will correspond to different geometry. Okay, So these are the postulates. Okay. Now, so after putting these postulates, so there were some drawbacks. Okay. So this failed at some moment. So what are the limitations or what are the drawback of this theory? So we have seen the postulates. So depending upon the postulate, so there were something which was missing. Okay. So this theory could not it could not succeed. Okay, it could not succeed to explain the bonding in complex compounds. So what were the limitation? The first one was that it did not give electronic interpretation for the formation of complex ion. So how the electrons are bonded, okay, in the complexes, it could not explain the electronic structure. So this was the first point. That is the electronic structure or electronic interpretation could not be done, okay, for the complex ion. Then it could not explain why secondary valencies are directional. Okay, so it could not explain. So we said that secondary valencies are directional and only why certain elements could form complexes. So this theory it could not explain. So it could not explain why only certain elements were forming the coordination compound. Okay, and why the secondary valencies are only directional. Then the magnetic properties and the optical properties of the complexes could not be explained. Okay, it could not explain why the color of the complex is this, why the magnetic property is this, and what is the optical property. So it could not explain these properties of complexes. Then it could not explain how a ligand can satisfy both primary and secondary valency simultaneously. So So these were the drawbacks of Werner's theory. So what he could not explain, he could not explain the electronic structure. Okay, he could not explain the electronic interpretation in the formation of complex ion. He could not explain why the secondary valencies are directional. He could not explain why only certain elements can form the coordination compound. He could not explain the color, magnetic property, optical properties of the complexes, and he could not explain why the ligands can satisfy both or how the ligands can satisfy both primary as well as secondary valency simultaneously. Okay, so these things he could not explain. So because he could not explain these things, then it gave rise to, so this was the electronic structure. Okay, Werner's modern electronic theory of valence. So this is okay, so because of this, because it could not explain the theory front, okay, so what happened? So they gave another theory. So the next theory was what? The next theory was the VBT theory. Okay, so because of the limitations of the Werner's theory, okay, because of the limitations of the Werner's theory, as he could not explain the Werner's theory, so because it could not explain the Werner's theory, then it gives rise to next theory, that is the valence bond theory. So what this theory tells you? This theory tells you the bond formed between the metal ion and ligand is purely a covalent bond. Okay, what is covalent bond? So what the VBT theory tells you? Valence bond theory. VBT means valence bond theory. Okay. So what this valence bond theory tells you? Valence bond theory, it tells you, okay, it tells you that the bond which is formed between the metal and the ligand, it is purely covalent. What do you mean by covalent, student? What do you mean by covalent? What do you mean by covalent? Yes, anybody? What do you mean by covalent? Covalent bond. How the covalent bond takes place? Covalent bond is what? Mutual sharing of electron takes place, right? Mutual, yes, very good. Yamuna has answered. So sharing of electron. So mutual sharing of electrons. Suppose HCl is there. So hydrogen, it has one electron in its outermost shell. So it will give electrons. Okay. And Cl. Okay. So it will give electron and this will take electrons. Cl will take electrons from H. So it will accept, okay, and this will lose. So this is a sharing of electron. So like this, the sharing of electron takes place. Fine. Very good. Shivaruni has also answered. So, valence bond theory, it tells you that the bond formed between the metal and the ligand, it is purely covalent bond. So, let us see the theory. So, what are the postulates which are given in the, or what are the points which are given in the valence bond theory? So, Linus Pauling. Okay, so who was a scientist who gave this particular theory, that is valence bond theory? It was Linus Pauling in the year 1931. In the year what? 1931. So what he said, so he explained the structure and magnetic properties of large number of coordination compound. So because in Werner's theory, it could not explain why the structure, why the magnetic property, okay, why it is showing diamagnetism, why it is showing it could not explain that. It could not explain the properties. So this was explained a large number of structures. Okay, a large number of coordination compound was explained by valence bond theory. Okay, so in the so let us see what are the points or what are the postulates which are given in this theory. The first one is that in the complex, the central metal ion, it provides definite number of empty orbitals. Okay, so the central metal ion which is present in the complex, okay, it provides definite number. So how many number of empty orbitals are supposed to be okay, so that the ligands will come and combine with the metal, so that it can form the coordinate bond. Okay, so that it can form what? It can form the coordinate bonds. So what is happening? So in the center, your metal is there. So this metal, okay, it provides the definite number of definite number of what? It provides a definite number of the empty orbital so that it can form the coordinate bonds. Okay, so that it can form the coordinate bonds. Second point, the number of empty orbitals, okay, which are provided by the central metal ion, it tells you the coordination number. Okay, it tells you the coordination number. Coordination number means what? It tells you the secondary valency. It tells you what? It tells you the secondary valency. So now, so first one is what? How many empty orbitals are required for combining? It is provided by the central metal ion. So the whatever the number of empty orbitals are there, so that is equal to the coordination number of the central metal ion. So which are the orbitals? S, P, D and F. So these are the orbitals. So depending upon how many ligands are present, so that much the metal will provide the number of empty orbitals. So these empty orbitals, okay, which are provided by the central metal ion, it tells you the coordination number. It tells you the coordination number of the metal ion. Okay, so these are the 2 points. Next point. So the metal ion. So when it provides the empty orbital, so this metal ion, when it comes under the influence of ligand, okay. So what does metal do? It provides the empty orbitals. Now this metal ligand, when it comes in metal ion, when it comes in contact with the ligand, what it does? These ligands, they use this empty orbital. Whatever the empty orbitals are provided by the metals, so they are used by what? They are used by the ligands. Okay, so which are the empty orbitals? Just now I told you S, P, D and F. So these are the empty orbitals, and these empty orbitals, they are used for hybridization. Okay, hybridization means what? Hybridization means it gives you a new set of orbitals. Okay, so whatever the empty orbitals are there, so these are occupied. So whenever the ligands come in contact with the metal, okay, so whatever the empty orbitals are provided by the ligand metal, so they are occupied by what? They are occupied by this ligands. So these ligands, they will undergo what? They will undergo hybridization. Okay, when they come in contact or when they come in influence of the metal. Okay, and they will give you hybridization. So what do you mean by hybridization? Hybridization means what? Whatever the atomic orbitals are there, okay, atomic orbitals, they will be of different energy level. So S, P, D, and F, right? So these are different orbitals. So they will provide different energy. So whatever the orbitals are there, atomic orbitals are there, they will produce a new set of orbitals, and these new set of orbitals, they are called as the hybrid orbitals. So in this hybrid orbitals, what will have? They will have definite spatial arrangement. So whatever the orbitals are produced, okay, for hybridization, they will give you a proper equal number of hybrid orbitals, and these equal number of hybrid orbitals, they will have definite spatial arrangement. Whatever the arrangement is there, that is, there is no repulsion, there is no, okay, there is no repulsion, there is no this what there is no repulsion, there should no, so the proper arrangement. Suppose we have two ligands, okay, metal, when it comes in contact with two ligands, so metal will be in the center, and what will happen? The two ligands will be at the two corners of the, so it will have a proper, so that it does not have any this what repulsion between these two ligands. Okay, so it will have a proper arrangement, it will have a proper spatial arrangement. So what are the different geometry or different arrangement? So it will have a tetrahedral arrangement, it will have a square planar arrangement, okay, it will have a octahedral arrangement. So like this arrangements are possible. So because of, so depending upon the vacant orbitals, so they will form number of hybrid orbitals, and these hybrid orbitals, they will form what? Proper orientation, and it will give you a different geometrical arrangements. Okay. So these hybrid orbitals, whatever the hybrid orbitals are there, okay, whatever the hybrid orbitals are there, which are produced by the metal when it comes in contact with the ligand, so these hybrid orbitals, what will happen now? They will overlap with the ligand. They will overlap with what? They will overlap with the ligand orbitals. And what will happen? These ligand orbitals, they will donate, what they will donate? They will donate the electron pair. Okay, they will donate the electron pair for bonding. So what is happening here? So hybrid orbitals, okay, whatever the hybrid orbitals are there, they will overlap with the ligands. These ligands, what they will do? These ligands, they will donate the electron pair for bonding. Okay, so this is the next point. So vacant orbitals, whatever are there, they are filled with the ligands and they form the coordination bond. So for bonding, how they can form? So metal and ligand, they form the bond. Okay, so this bond is called as what? It is called as the coordinate bond. It is called as what? Coordinate bond. So if the while we are using the hybridization, different orbitals, okay, if we are using the different orbitals, if we are using the n minus 1 d orbital, okay, if we are using n minus d orbitals, then the complex is called as the inner orbital complex. Please remember this. So when we are solving the complex, then you will come to know. So when we are making use of n minus 1 d orbitals, then it gives rise to, during hybridization, okay, then it gives rise to what? It gives rise to inner orbital complex, okay, or they are called as the low spin complex, or they are called as what? Low spin complex. Okay, so this is about the this. And if we are using nd orbitals, if we are using what? If we are making use of nd orbitals, if you are making use of nd orbitals, okay, nd orbitals, then what will happen? Then the complex is called as the outer orbital complex, outer orbital complex, outer orbital complex, okay, or they are called as the high spin complex. They are called as what? High spin complex. Got it? So this is the hybridization. So whenever the hybridization, so the empty so what so just I will recall. So what is happening in VBT? So there is a in VBT what we are explaining, we are explaining the metal and the ligand bond. Okay, so let me explain it once more in short. Okay, now let me explain it in the short. So what we are explaining in VBT, so VBT is what? So VBT, okay. VBT is valence bond theory. Okay. Now what we are explaining in valence bond theory. So valence bond theory, okay. So we are explaining the metal ligand bond. Okay. So we are explaining the metal and ligand bond. So this metal ligand bond, it is said to be a covalent bond. Okay. It is covalent coordinate bond. So it is assumed, okay, assumed that it is purely a covalent coordinate bond. Okay. Now, according to this theory, it is said that the metal ion, okay, the metal ion, what it will do, the central metal ion, it will provide empty orbital. Okay, it will provide number of empty orbitals. So what it will do, it will provide the number of empty orbitals for for formation of for formation of coordinate bonds. Okay, so that it can bond with the ligands. So this is providing empty space. Now, if you want to welcome some guest in your house, okay, if you want to welcome some guest in your house, okay, so what you will do? So you have two bedrooms. Suppose you have two bedrooms. What you will do? You will see that one bedroom, at least one bedroom, you will keep it free so that the guest will stay there. Okay, they can accommodate that. So what we are doing, what we are doing, metal is there. Okay, it wants to invite the ligand. Okay, so that the metal ligand bond is formed. So that the ligand comes inside. So for ligand to come to stay with metal, it requires space. Okay, it requires space. So how this space is given? So the metal is providing that space. Okay, how it is providing space? By giving or by providing some empty orbitals. It is keeping some house empty. Uh, it is keeping some rooms empty in his house so that the ligand when it comes, so like that. So central metal ion, what it is doing, it is providing the number of empty orbitals, and these empty orbitals, okay, so that it can form the coordinate bonds. Then whatever the number of empty orbitals are provided, okay, so number of empty orbitals, so which are provided, it will correspond to what? It will correspond to the its coordination number. It corresponds to its coordination number. Okay, it corresponds to what? It corresponds to its coordination number. So whatever the number of empty orbitals are there, it will tell you the coordination number, or it will tell you the secondary valency, okay, of that particular complex. Fine. Third one, so when this central metal ion, when it comes in contact with what? When it comes under influence, I'll not write contact, I'll write it as influence. When it comes in influence, okay, when it comes in influence of ligands, when your central metal ion, when it comes under the influence of ligands, okay, it will use, what it will do, it will uses the empty orbitals. Okay, it uses the empty orbitals. So which are the empty orbitals? S, P, D, and F. Okay, so for what? For hybridization. Hybridization means what? The hybridization means your metal and ligand will bond to form the what? so that it can form the coordinate bond. So hybridization takes place. Okay. So hybridization. So it uses the empty orbitals for hybridization and gives what? New set of. Okay. It gives new set of equal number of hybrid orbitals. Okay. It gives you equal number of hybrid orbitals, and these hybrid orbitals, they will have proper, they will have what? Spatial arrangement. They will have spatial arrangement. Okay. So which are the different spatial arrangement, like tetrahedral? Okay. Then square, planar. Okay. Then you have octahedral. So these are the different arrangement. Okay. Then next point is what? These hybrid orbitals, what is provided? Okay. These hybrid orbitals, what is done? It will overlap. Okay. It will overlap with what? It will overlap with the ligand orbital. So ligand will also have some what is that? So when the ligand is entering your metal ion, so when it is entering into the home of metal ion, so it will have also its luggage with it, right? So hybrid orbitals, what it will do, whatever the empty space is given by the metal, so that it is occupied by the ligand's luggage. Okay, like that. So ligand orbitals also will overlap with the hybrid orbitals, and what it will do, it will donate. What it will donate? It will donate electron pair. So ligands, what it will do? It will donate electron pair for bonding. Okay, it will give the electron pairs for bonding. So suppose, so when we are, so while if you are using the n minus 1 d orbitals, okay, when you are using n minus d orbitals for hybridization, it forms inner orbital complex. What it forms? Inner orbital complex. Okay, or they are called as low spin, or they are called as low spin complex. And if you are using nd orbitals, if you are using nd orbitals, then it gives rise to outer orbital complex. What it gives rise to? Outer orbital complex, or they are called as high spin complex. Okay, or they are called as high spin complex. So this is about your valence bond theory. Is it clear? Yes, is it clear about valence bond theory? So this is the short points I have given you so that it will be understood by you. Okay. So we have discussed the valence bond theory. So we have gone through the uh, okay. So here you can see. So here, so what are the valence orbitals? So these are the valence orbital which are provided by the cobalt. Okay, these are provided by the cobalt. Now cobalt is what? 28, right? So it is 3D. Cobalt is not 28. Cobalt is 27. Okay, so 3D7 4s2 something. So cobalt, when it undergoes +3, so cobalt, okay, now here, so cobalt, it will show what? Cobalt, it will have d orbitals 1, 2, 3, 4, 5, and 4s orbitals. Okay, cobalt, when it has, so 1, 2, 3, 4, 5, 6, and 7, and 2s orbitals, right? So what is happening now here? Let me write it properly. So cobalt is 27. So 1, 2, 3, 4, 5. 37. So 6 and 7. And here 2 orbitals, right? Okay, so argon 3d7 4s2, yes. So 1, 2, 3, 4, 5, 6, 7, and these 2 electrons, right? So these 2 electrons. So it is 4s2 electron, and this is 3d7 electron. So now when cobalt undergoes plus 3 oxidation, cobalt when it undergoes plus 3 means what? What do you mean by plus 3? Plus 3 means loss of 3 electrons. Plus 3 means there are loss of 3 electrons. So how the electrons will be lost? Yes, how the electrons will be lost? So 3d7 is there and 4s2 is there, right? So when it undergoes plus 3, so first the 2 electrons are lost from 4s. So 2 electrons are gone, and from here 1 electron. So how much it will be left? So when it is plus, that is your cobalt plus 3, it will be in 3d6. Okay, it will be in 3d6 and 4s0. 3d6, 4s0. So 3 electrons are lost. So let us write. So 1, 2, 3, 4, 5, and 6. Okay. So this is the okay. Now what we are doing? So now suppose depending upon the number of ligands, suppose there are 6 ammonia. Now if 6 ammonia wants to enter this cobalt's house, now what it will do? Cobalt. So cobalt will get paired. Okay, so when it comes in contact with the 6 ammonia, so what it will do? So 1, 2, 3, 4, 5. So what it will do? It will suppose it wants, so it is welcoming 6 ligands, okay, 6 ammonia ligands. So what it will do now? So suppose, so 1, 2, 3, 4, 5, and 6. So it will form like this 6 ligands. Now the remaining, so only 3 this is there. So what we are going to use? We are going to use the next set. So after 3d 4s 4p will be there. So 4p is there, okay. So now how many these are there? So these are the 1, 2, 3, 4, and 5, and 6. So it will show this type of hybridization. Okay. So D2sp3 like this. So like this the hybridization is shown. So that all we will discuss. So like this. So just remember. So like this the. So when it wants to occupy the 6 ligands, so it will empty the 6 hybrid orbitals. So these are the vacant d orbitals. Now here, if it is using the inside orbitals, now here it is using the inside orbitals. So it is called as the inner orbital complex. If it is using the nd orbitals, then it is called as what? Outer orbital complex. So these are the things. So if it is having a SP geometry. So if the coordination number is 2, if the coordination number is 2, then it will give rise to SP orbital, hybridized orbitals will be SP, and the geometry will be linear. So you can please note it down. You can take a screenshot of this. Very important. So geometrical shape, it depends upon the hybridization of the metal orbital. So if you have a coordination number 2, okay, then the geometry will be linear. So these are the complexes. Then if you have a coordination number 3, the hybrid orbitals used will be sp2. sp2 means what? One s orbital and two p orbitals. So one s and two p orbitals. So sp2. So sp2 like that. So if the coordination number is 4, if the coordination number is 4, then it is going to use how many orbitals? It is going to use s, okay, and p3. So S and P3, right? So 3P. So how many it is? 1, 2, 3, and 4. So 4 hybrid orbital, and it is sp3. sp3 hybridized orbital. So what type of geometry it is? Octahedral. So these are the complexes which will show octahedral. This is a, when you have sp2, it will show a trigonal planar. Okay, linear means like this. So metal will be in the center, two ligands at the octahedral, so two corners, and this is your trigonal planar. Tetrahedral, so tetrahedral is metal here, and this is tetrahedral. Okay, then if you have 4, again coordination number 4, and if it is using dsp2, so if it is using the inner orbitals, then it will give rise to square planar. So these are the complexes for square planar, and if the coordination number is 5, then it is going to give dsp3. Okay, then so it will give you a diagonal bipyramidal. So these are the geometries. So please note it down. So this just now we have told. So if it is using the inner d orbital, so if it is making use of the inner d orbitals, it is giving rise to inner orbital complex or spin low spin or spin paired complex. And if it is using the outer d orbitals, okay, then it is called as outer orbital complex, high spin or spin free complex. So these things, is it clear up to here? So the some of the applications, okay, of the VBT. So that we'll be discussing in the next class. So we are left with a very short time. So it will not complete. So whatever the compounds which we are going to study, complex compounds, so that we will discuss in the next time. Any doubts up to here? So we have discussed today about the VBT, and Werner's theory. So Werner's theory followed by the VBT. Okay, so the applications of your VBT. So that we'll be discussing in tomorrow's class. Any doubts up to your? Yes. Yes. Any doubts? Fine. So I shall end the session here. Okay. So we'll meet in tomorrow's class. Yes. Thank you. Have a good day.